in the last few lectures we had seen various arithmetic algorithms and techniques using which we can carry out various operations on integer numbers. Specifically, we looked at the design of adders, subtractors, we looked at the design of multipliers and also dividers. So, there we had seen basically how operations on integer quantities can be carried out. Today, we shall be extending that concept, and in this lecture we shall be specifically talking about something called floating point numbers, where we can handle fractional quantities as well. So, the topic of this lecture is floating point numbers. Okay, let us see the motivation first. Well, here as I said, we want to represent a binary number with a fractional part. So, in general, any binary number with a fractional part can be represented like this, where this B0, B1, these are the binary digits, this dot is the binary radix point. So, this side you have the integer part and this side you have the fractional part. So, if you want to convert this binary number into the equivalent decimal, so you recall that every binary position has a weight. B0 has a weight of 2 to the power 0, B1 has a weight of 2 to the power 1 and so on. Similarly, on the fractional side, B minus 1 has a weight of 2 to the power minus 1, B minus 2 has a weight of 2 to the power minus 2 and so on. So, you can write the decimal equivalent of this number as this, the digit multiplied by the weight 2 to the power I, where I can vary from minus m up to n minus 1. This kind of a representation is also called fixed point numbers, because the position of this radix point is fixed in the number representation. But if we allow this radix point to move, not fixed in a particular position, then we refer to this number representation as a floating point number representation. So, this is the basic idea behind the so called floating point number representation. So, let us look at some examples. Well, here I will tell you why I have taken specifically these examples. You look at some binary numbers with fractional parts 1011.1. So, if you want to convert it into decimal, you will have to multiply each digit position by its weight 2 to the power 3, 2 to the power 2, 2 to the power 1, 0, and for the fractional part 2 to the power minus 1. So, the value becomes, if you just calculate, 11.5. Similarly, this number 101.11 will have a value again multiplied by the weights, this will be 5.75, and if you take a number 10.111, so the weights will be this. So, on the fractional part it will be minus 1, minus 2 and minus 3. So, the value will be 2.875. Now, one thing you see across these numbers, these examples I have taken, that the decimal point is actually shifting left by one position from this number to this number to this. So, when the decimal point or the radix point shifts left by one position, if you look at the corresponding value, you see that this means a divide by 2 or division by 2. 11.5 if you divide by 2, you get 5.75. 5.75 if you divide by 2, you get 2.875. So, shifting right by one bit, that means if you move this radix point to the left or right, this will mean divide by 2 or multiply by 2. Okay. So, if you move the radix point to the left, it will mean divide by 2. If you move the point to the right, it will mean multiply by 2. Okay. And another point to notice that if we have a number of this form 0.11111, this will have a value less than 1. Why this? You see, If I write such a number 0.111, say there are several digits, binary digits. So, if you look at the weights, it is 2 to the power minus 1, then 2 to the power minus 2, then 2 to the power minus 3 and so on. You see, this is a GP series. This is actually half plus 1/4 plus 1/8 plus like this. So, if you calculate the sum of this GP series, first term into 1 minus common ratio is half 1 by 2 to the power n, if it is up to n terms, divided by 1 minus common ratio. So, half and half cancels, this is 1 minus 1 by 2 to the power n, where n is the number of digits. So, you see, as the value of n increases, as we increase this number of digits 1 1 1 1 1, the value of the second quantity tends to 0, because 2 to the power n increases rapidly. So, this is a fraction you can write as 1 minus a very small value epsilon. This actually tends to 1, right, as n tends to infinity. So, this is exactly what we are meaning here. A number which is of this form will always have a value less than 1. In the limit, it will approach 1. Okay? All right. Now, in the representation, there are some limitations. Let us look at this now. In the fractional representation in binary, if you look a little carefully, you will see that only numbers which can be represented in the form x divided by 2 to the power k, where the denominator is some power of 2, those numbers can be precisely represented in binary, like 3 by 4, where 4 is a power of 2, you can express as 0.11, 7 by 8, 8 is a power of 2, 0.111, 5 by 8, 0.101. But if the denominator is not a power of 2, like here I have taken examples of 3, 5 and 10. So, if you go on expanding decimal into binary, you will see that it will never terminate. So, this 1 by 3, this 10 10 10 alternates, 1 by 5 you see 0011 0011 alternates, this 1 by 10 also you will see after some point 0011 0011 keeps alternating. Okay. So, more the number of bits we use for the representation, more accurate will be our representation. But one thing we should also remember, that when you are representing 1 by 3 in a computer like this, so we have a finite number of bits to represent. Okay. So, we can never represent 1 by 3 exactly. So, it will be very close to 1 by 3. Okay. So, the point is that you are not able to represent some of the fractions in a precise way, there is an error in the representation. So, by virtue of that, what might happen is that, suppose in a program you are dividing 1 by 3 and the result you are again multiplying by 3. So, you expect that the final result should be 1, but you might see that the final result is not 1, but close to 1, and this is because of this rounding error, truncation error you can say. You have finite number of bits to represent. This 1 by 3 you cannot represent precisely. Okay? Fine. Now, let us come to the so called floating point number representation, well, which is around for quite some time, and IEEE has come up with a standard. So, whatever we shall be discussing will be basically based on this standard. So, let us try to see what this standard says. Firstly, we already talked about the fixed point representation earlier. So, there we had said that if we have a number with a fractional part, then we can have n bits in the integer part and m bits in the fractional part. So, the radix point is fixed, but in this representation we have limited amount of flexibility. Why? Because you cannot represent, for instance, very small or very large numbers which occur very frequently in scientific computations. Like for instance, I want to represent a number 2.53 into 10 to the power minus 26 or 1.7562 into 10 to the power plus 35. These kind of numbers where either the number is very large or the number is very small, after the radix point there are many zeros, after that only the significant digits will start. So, these kind of numbers you cannot represent in a finite number of bits where the radix point is fixed in a location. Okay? For this you need something else. So, what is the solution? Solution is to use the so called floating point number representation. Here a number f is represented as a triplet S, m and e, where the value of the number is minus 1 to the power s m multiplied by 2 to the power e. So, m is some sort of a magnitude, 2 to the power e is a multiplier and s actually represents the sign. Okay? If s is 1, number is negative, if f is 0, number is positive. So, coming again to this representation, as I said, s is the sign bit. So, this represents or indicates whether the number is negative, for that s is 1, or it is positive, for which s is 0. This m is conventionally known as the mantissa, and I will explain a little later why. This mantissa is usually a fraction which is in the range 1 to 2. The minimum value is 1, maximum value is 2. How? I shall come. And e 2 to the power this number, this is called the exponent, which is weighted, as you can see, by a power of 2, 2 to the power e. And in the IEEE floating point format, you can have either single precision numbers or double precision numbers. The general format looks like this. The number starts with the sign bit, followed by some number of bits for the exponent, and finally some bits for the mantissa. For single precision numbers, the total size is 32 bits, for e you have 8 bits, and for m you have 23 bits. But for double precision numbers, you have 64 bits in total, where e is 11 bits and m is 52 bits. Okay. Now, just going back once, the number of significant digits in your representation, this will depend on how many bits you are using for the mantissa. This is the number of significant digits. It will depend on how many bits you have in m. Now, although for single precision number, let us say for single precision, we have kept 23 bits in the mantissa, but actually the idea is as follows. The mantissa is represented as a number which always starts with a 1, and there is a implied radix point here, and after that you can have anything 0 1 0 1 1 1, anything after that. So, the first digit is always 1. So, what we do because of that, this bit you assume that this is an implied bit, and because it is always 1, you do not store this, you store only the remaining number of bits. So, here for single precision there are 23 bits here, but if you also count this 1, it becomes 24. So, the number actually is a 24 bit number, but because it always starts with a 1, you are actually storing 23. Okay. So, when you are calculating, you will be assuming 24 bit mantissa, because that implied 1 bit is also there. Now, how do we calculate number of significant digits? It is very simple. In binary you have 24 bits, in decimal how many bits? So, you use this equation 2 to the power 24, so many combinations equal 10 to the power x. You take logarithm on both sides, log 10 to the base 10 becomes 1, and log 10 base to the 2 is about 0.3. So, if you multiply this log 10 2 with 24, x becomes about 7.2, which means in decimal you can have 7 significant digits. But if you think of double precision number, where for mantissa you have 52 bits, so 52 plus 1, this will be 53. 53 multiplied by log 2, so it will be much larger, about 15 or 16 digits you will have, okay, for significant digits. Similarly, for exponent in single precision number, you have 8 bits, and this exponent can be either positive or negative, 2 to the power plus something or 2 to the power minus something. This 8 bit is actually you can regard it as a 2's complement signed integer. Range will be minus 128 to plus 127 in 8 bits. Okay. So again, if you want to find out the range in decimal, you follow a similar calculation. 2 to the power 127 is equal to 10 to the power y. If you similarly calculate, you will find y comes to about 38 point something. So in decimal, equivalently you can have maximum exponent value as 38, which means you can, in the single precision, you can represent up to 7 significant decimal places, and the range of the number can be 10 to the power 38 to 10 to the power minus 38, right. Okay. Now, in floating point number, there is an interesting concept called normalization. Let us look at the encoding part of it, that how the exponent and mantissa are actually stored or encoded. Let us assume that the actual exponent of the number is exp. So, the number is m multiplied by 2 to the power exp. So, we are encoding this exp in some way and we get e, which is stored. Now, with respect to e, the value of e can range from 1 up to 254. It is an 8 bit number. In 8 bits, you know, for unsigned number the range is 0 up to 255, but here we are saying 1 up to 254, which means we are leaving out 0 and 255. So, the all 0 and all 1 patterns are left out, they are not allowed. So, how we are encoding e? You have your actual exponent exp, we are adding a bias to it. You see, exp can be either negative or positive, but after you add this bias, e becomes always positive. So, how much is the bias? For 8 bit exponents for single precision, you take the bias as 127. So, because you see, I mean again, if you look at the value of the actual exponent, it can range from minus 128 to plus 127. Now, this one combination you leave out, let us say it is from minus 127 to 127, because the all 0 all 1 pattern we are not using. So, if you add a bias 127 to it, so minus 127 plus 127 becomes 0 and 127 plus 127 becomes 254. So, this is positive. So, the actual exponent we are doing a biasing, you are generating the value of e, which is an unsigned positive number. Okay. This is how we are encoding e. So, the bias is 127 for single precision and it is 2 to the power 11 minus 1 which is 1023 for double precision, because in double precision we have 11 bits for the exponent. Now, for the mantissa, as I had said earlier, we encode the mantissa in such a way that it always starts with a leading 1, and whenever we encode mantissa in this way, we say that the number is normalized. If the mantissa starts with 0, we say that it is not normalized, right. And the remaining bits, this XXX, these denote the bits that are actually stored. Because the first bit is always 1, we do not store it explicitly, we are getting this extra bit for free. We are storing only the remaining 23 bits, let us say. Okay. So, when the value of x is all zeros, the value of m is minimum 1.0000, the value is 1. When x is all ones, that means 1.11111. So, as we saw earlier, 0.11111 is a value which is very close to 1. So, the value of this number becomes very close to 2 minus a very small value epsilon. So, you recall we mentioned earlier that the mantissa m will be having a value between 1 and 2, and this is why it is so. Okay. Fine, let us look at some encoding example. We consider a number f, let us say 15335. If you convert this into binary, it is like this, and if you express it in fractional form, so if you put a decimal point here, a radix point here, so if you count the digits into 2 to the power 13, there are 13 binary bits here. So, this is same as this. Now, if we express the number like this, you see the mantissa is already normalized. Okay. So, it starts with 1. So, you are not storing this 1, you are storing the remaining bits. So, the mantissa will be stored as this. So, there will be how many bits will be there for the mantissa? 23 bits, and exponent is 13. So, bias for single precision is 127. So, the actual value of E will be 13 plus 127, which is 140, which in unsigned binary is this. So, this number will be stored as sign positive followed by exponent followed by mantissa. So, if you divide this number into 4 bits and convert it into hexadecimal, you will see it starts with 0100, which is 4, then 0110, which is 6, again 0110, which is 6, 1111, which is f, and so on. So, in hexadecimal you can express it like this. Let us take another example where the number is negative minus 3.75, which in binary you can write like this, and if you express in normalized form, push the decimal point here, it becomes like this. So, we will be storing the mantissa as only this 111, this one we do not store, and the remaining zeros, and exponent exp is 1, you add the bias, it becomes 128, which is this. So, the number will be represented as sign is 1, negative, exponent and mantissa, which in hexadecimal is actually I think this is not 4070, this will be 110, this will be C070, this will be C, not 4, okay, 110, this will be C070. Okay. Now, some special values are supported. When we saw earlier, we mentioned that the values of E, which is all zeros and all ones, they are not allowed in actual numbers. Okay. But what happens when the value of E is all 0 or all 1? So, these are the so called special values. Let us see. So, when E is all 0, then if M is all 0, this combination represents the special number 0. So, you see the number 0 is represented as an all 0 string. This is one way of representing 0, so that it can be easily checked by hardware. And for E all 0, if we have a mantissa which is not all 0, this represents some numbers which are very close to 0, because see E is 0 means it is already in biased form, it means 2 to the power minus 127. So, after adding 127 you are getting 0, right. So, the number, the magnitude of the number is really very small. So, here we are representing numbers which are very close to 0 when E is all 0. These are sometimes called denormalized numbers, okay, because if M is all 0, you do not have a 1 at all, you cannot make the first bit 1. So, for this denormalized numbers, your exponent has to be all 0, meaning that this is a special kind of a number where the mandatory requirement of the first bit of the mantissa is 1 is not to be assumed in this case, okay. And 0 is represented by the all 0 string, as I had said. And when E is all 1, there is an interesting thing, then the all 0 combination of the mantissa represents the value infinity. This is a representation in the IEEE format, and any value which is not equal to 0, this represents an invalid number, which means not a number. Sometimes it is called NaN. Why it is required? Because you see, there are certain cases where you do not know the value of a number, like you have defined some variables but not initialized them. So, to start with, they will be having NaN. Say infinity, you are multiplying by 0, this is undefined. Infinity, you are subtracting from infinity, you are trying to find out square root of a negative number. So, all these are examples where the result is supposed to be a NaN, and IEEE format allows this special value to be stored and represented like this. So, in this scale, the summary of number encodings, you can see that in the between, when you have the mantissa values all 0, you have the number 0. So, there are two representation of 0, plus 0 and minus 0, and for very small numbers you can have denormalized numbers, and when you have normalized numbers it will be beyond that, and you can go up to plus infinity. Plus infinity is a special representation, minus infinity is also a special representation. Beyond that you have invalid numbers which are not a number, right. This is how you can summarize the encoding. Now, there is another feature of the IEEE format which is also very much useful. This is called rounding. Now, suppose when we add two numbers, let us say in single precision. So, normally we add the mantissa value after aligning the exponent. What do you mean by exponent alignment? Suppose my one number is 1000 into 2 to the power 2. Let us say other number is 1.011 into 2 to the power 1. So, when I want to add, I cannot straight away add because the exponents are not same. What I do, the second number I make it 2 to the power 2, and for that I have to shift my decimal point to the left by 1 position. So, it becomes 0.1011. Then I can add 1.100 with this. So, I will get the result. Okay. This is what is mentioned here. We add the mantissa value after shifting one of them. So, we shall be coming to this again. So, after adding, the first 23 bits of the sum is taken and the remaining bits are discarded. This is called the residue. Now, IEEE format supports 4 different rounding modes. One is the normal thing, truncation. Beyond 23 bits, you just discard the remaining bits. This is truncation. Rounding to plus infinity is the second mode. What it says here is that you look at R, if you see whether R is greater than equal to 0.5 or not. If R is greater than equal to 0.5, just like ceiling function, if it is so, you increase mantissa by 1. Similarly, if it is less than 0.5, so you will be rounding to minus infinity, you move it to the next lower integer value. And second one is a rounding. So, depending on the value of the R, here you are either moving it to the next higher or the next lower, and rounding means if it is 0.5 or higher, you move it up, otherwise you move it down. This is rounding to the nearest. So, to implement this, 2 temporary bits are used in the representation. One is called round bit, which is the most significant bit of the remaining residue R, and sticky bit S. The value of S is actually the logical OR of the remaining bits of R other than the MSB, okay, the remaining bits. Now, you can take the decision, and accordingly which rounding mode you use, you can implement by knowing these values, that whether R is greater than 0 or not, you can know it by seeing if either R or S is 1, plus means logical OR. R is exactly equal to 0.5 means R is 1, but S is 0, that means remaining bits are 0. R is greater than equal to 0.5 means both R is 1 and also S is 1, dot is logical AND. So, after you check this, depending on which kind of rounding method we use, you may have to do a renormalization of the number, so that the mantissa first bit becomes 1. So, I have left some exercises for you to solve. These are very simple examples like that. Like the first one I tell you, this is representation. First one will be your sign bit, 0 means it is positive. So, next 8 bits 0 1 1, 1 1 1 1 1, this will be the value of E. So, you will have to subtract 127 from this to get the value of EXP, and the remaining value will be your mantissa, it will be 1 point this. So, that will be the value of your number, right. So, in this way you can just work out the other examples also. So, we have seen basically some representations of floating point numbers, and in particular the IEEE format, which is almost universally used nowadays in almost all computer systems. So, we have seen how numbers are represented, how some special numbers are represented which are very useful during calculations or computations, and also how we can do rounding of the numbers, right. So, with this we come to the end of this lecture number 38, and in the next lecture we shall be starting a discussion on how we can carry out arithmetic using floating point numbers. In this lecture we have looked at just the representation. Later on we shall be seeing how we can carry out addition, subtraction, multiplication and division on floating point numbers. Thank you.